Good morning, everyone. I hope all of you are doing fine and well and ready to dive into a new topic, which we briefly touched last time. But how does everything connect in the semiconductor world, right? So, we are going to talk about interconnection at different levels because we were looking at just an example of, let's say, like a system of, let's say, NVIDIA, where we saw that there were multiple GPUs, CPUs, whatever are there. There are memories which could be there on the chip, right? So let's say this is a computing unit. These are your memories, right? So a lot of that could be there on the chip. And now the question you would ask is that how do I interconnect all of them? And why do interconnections matter? Because you know from your experience, if you are connecting from one city to another city, what do you check? Google Map. You try to find what is the shortest route, right? What is the route in which I will take lesser time given the traffic? So all of that is very important, and that is why you would see that there are different strategies of interconnect one would use at different abstraction levels, right? So let's first talk about from a very basic level where all this starts, which is a chip, right? So that is what we have talked about. And we also last time briefly touched on this in the video where we were talking about that why 3D matters, right? So why things are turning 3D or things will turn 3D in future in the chips is the reason is uh, and in during that conversation what we talked about is that if I have this large silicon, right, uh, for example, which is as we discussed, this is a part of a wafer, right, coming from a wafer, right? A wafer is a 12-inch wafer, for example. As of now, is 300 millimeter diameter, and out of that there is one chip. The size of this chip could be anywhere, let's say 10 mm by 10 mm, so which is 1 centimeter by 1 centimeter. And this is just rough size, right? This could be bigger as we discussed, but and this is around 775 micron, right? And so then you see that on this substrate is what you are assembling these different tiny transistors. So this is your one transistor, right? The metal oxide semiconductor, all of that. So this is a zoomed out picture of that transistor I'm showing, but there are these multiple transistors which are there on the substrate, right? Which are made on the substrate. So now you see you need interconnections to do that, right? You need ways to connect them, and that is where all the idea of that this backend of line which we use is that you are using pathways which are right. So you are using some layers of which are, we can call it the bonding layers, right, which are your backend of line layers, or right. So this is for the signal interconnect, I mean this is for interconnection, right? Interconnections. So that means what you can do is now you can connect this transistor to this transistor, let's say, and like that, right? So depending on where, how far you have to go, you will go to a particular highway, because, and that depends on, now there is a lot of, and we discussed is that this is a problem in computer science known as routing, or in physical layout called routing, and you have to figure out where you have less congestion, like the same thing which your Google Map does, right? Where do you have the less congestion? Where do you will have less fuel, right? Less fuel burning. All those things it would, which is the distance and everything, it would check, right? So depending on that, it would give you a right way of connecting these through multiple layers. What is distinct in these multiple layers? So we call these multiple layers as typically M1, M2, like that, right? So till M13. So currently, I think for the 2 nanometer node, we are seeing somewhere around 13, 14 layers of metal stacks, which are just there for connecting these billions of transistors, right? So now you will see that how do we connect them, right? Then you would see that, okay, if this M1, M2, what is distinct about these thing is that because we need many connections at the M1 level, the pitches means that if I'm drawing two line like this is called pitch, or the interconnect pitch, right? So this is your interconnect pitch, which means, and this is the width of the interconnect, right? This is the width. So then you see that the pitches, the how close you can make these lanes, right? That is what is the pitch basically. And at M1, you would see, because there are many transistors and you would like to connect them first at the M1 level, right? You don't want to go to M2 because it would take a longer route, right? So you would first, because the shortest route you will find is probably through M1. But the problem there is that the congestion could be a big problem, right? So your preference would be, and that is why this is the most aggressive pitch you will have, right? So least pitch you will find here, because you would like to make these shorter connections first. But then if you see, oh, there is a congestion, right, which is happening, what you would do, you would go to M2 and say, okay, this is more pitch than M1, right? The lanes are, let's say, sparser than M1. But what happens also, the of width of metal lines in M2 would be more than width of metal lines in M1, right? And this is what you are doing because you have more space. So the pitch is more, you are more relaxed as you go above and above. And that is what also results in, so if you know a little bit about the resistance of a metal line, let me just briefly talk about the metal line. So this is a metal line, this is the length of the metal line, this is the cross section of the metal line, which is the width and the thickness, right? So that is how the metal line looks like, which is a 3D cuboid kind of a figure. And you see this length depends on obviously how long you are going, but the width depends, as we saw, it depends on which metal layer you are in, and thickness depends on these things, right, where you are putting these. Okay. So what we see, so yeah, let me just change the width and thickness so that, yeah. So then width is something you see that it can increase. Now, how does the resistance of this line play? It can be described in this term, and this we all know. This is rho L by A. Rho L and A is your W and T. So what you see is if you increase the width, resistance is going down, right? So that is a very good news because you are going a longer route, but your speed is faster, or your resistance is lesser. So why this resistance? Because this, when combined with C, which we have talked also, RC delays and everything in few videos, that plays a very important role, right? So that means now you go through and then you face less resistance if you, even if you take a longer path. That is what we can understand. And this kind of increases, this is the same trend which you see, the pitch here, metal pitch basically of M3 becomes more than metal pitch of M2, and obviously the width also of M3 becomes more than the width of M2, and that is what is kind of followed throughout. And then you see that if you are going longer, you don't have the same penalty which you are feeling in M1, because you are now trying to go through the least resistance path, but the problem is still you are going longer, right? So that is the, and then based on this optimization, the routing algorithm, you will find the most suitable path for you given the current circumstances in your design. So it changes from design to design, right? There is no fixed rule, and you have to check that for a given design. Okay, coming back to our picture. So the interconnections, we see clearly that this is much more complex than what you can imagine, right? And these congestion and everything, there are many, many metal lines in this back end of line, which we saw 13 metal lines, right? So just the sheer volume of transistors you are trying to connect, or the devices you are trying to connect, is just huge, right? And so now one of the key things we see typically in this metal lines, because if you see a transistor or a CMOS gate, right, which is made of two transistor, uh, there is a signal which comes here, right, which is what we know as Vi. This is V out. So this is a CMOS inverter, right, which you can find as a basic NOT gate. And I think we have talked about in uh, some video in DRAM, or when we were talking about probably transistors. Yeah, the different avatars of transistor, I think. And we talked about that, okay, this Vi is giving you this NOT operation. So basically this is Vi bar, right? This is the basic NOT gate one can build, and these two are supply lines. This is the ground supply line, and this is a your VDD or whatever your high voltage supply line, right? So that means you clearly see now distinction between two type of signals here. One is what we call as the power lines, right? And one is what you call as the sub signal lines. So signal lines, you see the VI and VO, they are your signal lines, and your power lines would be your VDD and VSS, right? Which is what you are going to see. Power lines are very, very important to look at, because what happens is, let's say this resistance we were talking about, we know that there is a current flowing through these lines, right? So there's a current flowing through this wire. And when we know that there is a particular resistance, there is going to be a drop in the wire, which is your current and into the IR, whatever is the wire. So that is the drop you are going to see within your wire. So let's say if you have a power line, you give power somewhere here, right? Let's say you are giving VDD here somewhere, and this is going through multiple lines and reaching this part, right? Because this VDD is supplied from outside, obviously. So then this path which is taking this VDD line, you see if it is very long, that means the resistance is very high. So for the same current, you will see that their drop will be much higher. So what you finally get, let's say VDD dash at the transistor or at the standard or this CMOS inverter would be much, much lesser than what you would desire to be, right? So that's a big problem, which is what we know as the droop, or the which is the IR drop, is a very simple way of I think the VLSI designer typically known as a IR drop. And there are multiple static, dynamic, different kind of drops and everything one can study. But now, what from the interconnect point of view, what is important for us to see that yes, this is a big problem if this takes a very long path. And that is why industry thought, okay, why do we need to provide this line from the top and we have to go through these 13 metal layers and reach there? Is there a much smarter way to do that? And that resulted into a thinking that, okay, is this possible that I have silicon, right? And I'm anyway, when I'm making transistor on top of that, I'm not using uh, for example, the 775 micron of silicon, right? Because only this part is used, let's say whatever is the active channel part, right? When I'm making these active devices, so this part is unused, right? The silicon. So why do I what can I use then if I'm using this to connect signals, right? Whatever signals I'm using, connecting all of these lines. For power, is it possible rather than providing it from the top, can I provide it from the bottom, right? So that means if I have the VDD which is going like this, then the VDD can go to this transistor from the bottom, right? So that means the VDD lines now, what you would see in the, so you will first thin down the silicon, right? Because you don't want signals to travel more. So obviously you will thin down the silicon from 775 to let's say 30, 20, 30 microns, right? So that you don't go the same way which you are coming. If you are coming, let's say the back end of line, for example, if it can be, let's say hundreds of microns, then you would like your bottom side to be lower. So that means the VDD can be provided here. And when it is provided here, then through whatever lines I'm reaching, I can reach the transistor, right? So that means you have significantly reduced the length of the VDD which it takes to reach there. And this is what we know as typically as the backside power delivery network. Okay. So that is very, very hot topic, delivery. And as I said, right, this whole series now we are turning into more on research that what is going on in the world, right, as of now. And for that, one needs to understand the basics. So that's why I'm telling you that if you need those basics to be reviewed, you can focus. Let's say you can look at the internet and different books which you have, or you can, if you still having a problem in understanding any basic concept, do let me know. I'll be more than happy to put a video on that, right? So this is the power delivery network, which is going on uh, uh, thing which is there. One of the thing which is a very important problem there, and we also work on one of this problem, is where we see that when we thin down silicon, what was happening earlier, all of this transistor are generating a lot of heat also, right? Because you know that there are resistances. Whenever there are resistances, there is a joule heating which is going to happen, which is your I square R losses, right? So this generates into heat, right? And this we have seen even the basic fundamental reason of this heat, and we saw this in the generation recombination video, what is happening when the electron is going up and down, right, in the semiconductor. So what we see, this heat is coming out, and it has to go from somewhere, otherwise there would be heat generated, and these metal lines will start melting if there is this accumulate, right, this heat. So there is one way people look at is obviously excavating this heat from the bottom and top sides, right, of the transistor. So that is the heat which is excavated. Uh, but now one of the problem view, when you thin down the silicon, what you are having is that because now you have silicon which had certain thermal conductivity, and it was going on through this region, right, this heat was excavated. Now because you have thinned down the silicon, and there is a lot of level of interconnections you have on the back, which is heavily dominated by metal and dielectric, right? Metal is very good conductor of, it can conduct heat, very high thermal conductivity, but dielectrics are not, right? So that means you are resisting, or there is some problem because of heat you could have on this backend of side network because of this thinning down of silicon. And this is one of the active area you can look at, okay, how much it is increasing, how can we optimize it, and on all of that, which would go on. Because so now what you see is that the problem is, in the future interconnection, it's not just about the electrical that you want to minimize the delay, it also becomes about thermal, right? And as you go along, you will see in this video that it may also become a very important problem of mechanical problem, right? So that is what becomes what we call is the multi-physics problem, right? And interconnects is a very good example of this multi-physics problem, that how things are becoming multi-physics right there. So this is a very brief idea of, at least till the BSPDN or the chip level interconnects, what is happening, right? And now we have to take this to also do the system level, and which we will do in another video, the second video. But this gives you a good idea of the interconnects, let's say, at the chip level, right? So that is what we have kind of looked at, that what defines this and what are the areas people are looking at to redefine this. So one of the key thing, if you want to work in this area, do think that now the problem is not just electrical. Obviously this comes as that you want low delay. So this is the wish list for interconnect, right? As we saw, lower lower delay means lesser R, lesser C. C is coming from when you're putting two interconnects, as we saw, right? You put two interconnects together, and you see these is one metal, this is one metal, but they are separate because these are, let's say, this is a signal which is, let's say, VI, and this is a signal which is VO. You have to isolate them. So there is a dielectric in between. And when there is a metal dielectric, we have seen this, right? Does this consist of? This consists of a capacitor. So you see that the capacitor also is becoming a big problem, right, in the interconnect, and one needs to look at this, the lower delay, and that is what your typically algorithms and everything is doing, right, when you are designing this. So that is one idea, to design better algorithms so that you can do that, right, so that this can be done in much better fashion. The another idea is that now we saw that we kind of divided this interconnect, right? Or you could find a much more way of structuring these devices. If suppose, for example, uh, there is a particular kind of devices which people know as SRAM, right? We had talked about this even in the last video. This is the cache which we know as, and what is the inherent in the SRAM is there is a structure of the MOSFETs, right? They are arranged in a certain way, right? So that means wherever there is a, in the particular cell, and in the cell there are, let's say, six transistors, they are arranged in a particular way. Okay, so when they are arranged in a particular way, and they have to be connected in a particular way, that then means that you can find much better strategy, because as soon as you have more determinism, right, more determinism in interconnect, that is much better for your that was going to be much, much better for your algorithms, right? Better designs and algorithms. Good. Because then your algorithm does not look for multiple solution optimization solution, because you have reduced the space and it does a much better job of optimizing it, right? So that is where more determinism, and this is what is typically known as something which you can look at in another field, is nano mesh, right? Which is how do you connect this, and there is a mesh which you create of the interconnect in a very interesting way, and the idea is just that you can pack in a way these things much tighter, and you have lesser distance you have to go, right? So lesser, you have to minimize the lesser distance, and this is directly coming from lesser distance means your resistance is lesser, right? And so that would be giving you fast interconnect, right? Maybe you can reach, and you will also lose the signal. What we talked about, the drop on this interconnects will be very, very less, right? So that becomes a very, very important guiding forces for these interconnects, and people have been looking how can we pack. So this becomes this determinism, how can we keep pack, and we have to also look at the lower distances which we are going, and lower delays also with which we are going. And another aspect we just looked at is the thermal aspect, that we have to look at, that how good these interconnects are from the thermal point of view. Are they able to excavate the heat, right? Is interconnect network able to excavate the heat, is another problem what would look at, because it has to excavate the heat, right? Heat from FUL, right? So that becomes very, very important forces for, let's say, minimizing or optimizing this chip level interconnects. And next, I think we will look at into much more at the at a higher abstraction level, that where does the chip level interconnect go, right? And what are the problems there? So that is what we are going to look at till the system, that what is happening in this. So this would take some few videos, right? So be with me, and I think in the next video you'll see another level of interconnects, and that is how we will go about talking about those. Okay, thank you, and happy learning to all of you. Keep learning. See you. Bye bye.